So we need to add 2 electrons. So then that means that the ion we're left with is S2 minus, so the sulfide ion. Okay. So yeah. So we'll talk about ions later when we talk about ionic nomenclature, probably. So until then, all you need to know is like, so this is very simplistic, but just try to achieve a noble gas configuration and try to do it in an energetically favorable way. So, okay. Let's see. So I think we have some time, so we can talk about a little bit more of the quantum stuff. Okay, so let's talk a little bit about light. So you might have heard that light is both a particle and a wave. And there are a series of experiments done that can justify this claim. So to show that it's a particle, just as an example, one experiment was the photoelectric effect. So, oh, by the way, did you know Einstein did not get a Nobel Prize for relativity? He did get a Nobel Prize on the photoelectric effect. So the idea behind the photoelectric effect is that you bombard this piece of metal with photons, and then electrons get kicked off, so we can detect these electrons. And the reason why this shows that light is a particle is that, for example, if light were a wave, then it would the wave would, compared to the size of the electrons, the wave is like huge, right? The wavelength is huge. So this is kind of like, imagine like you're on a beach and you just see a wave, and then it just hits a single rock, and then it pushes that rock up the beach, but then doesn't touch anything else, right? So this effect can't be explained by wave properties. It's explained by light being a particle that can like interact with the electron, okay? However, there are some experiments that also showed it was a wave. So the famous one would be the double slit experiment. So you have 2 slits and then you shine light through them. And then on the other side of the slits, you don't see 2 like beams of light. You see this diffraction pattern, which can only be explained by wave properties. Okay. So it turns out that light is an electromagnetic wave. So it's a wave in the electric and magnetic fields. And because of this, it interacts with charged particles, so electrons, right? So light can interact with electrons, which is the big point. So one more thing. So a particle of light has some energy, and this energy is equal to the Planck constant times nu, and nu is a Greek letter, and it represents the frequency of the wave of light. So like, if the wave is going up and down, how many times per second does it go up and down? So the frequency is like some huge number. Did I? Okay, one more thing. So then we use the symbol lambda. So, wait a second. So by the way, this is what lambda looks like. So lambda times nu, so the wavelength times the frequency, equals the speed of light, which we usually represent as c for Latin reasons. And okay, so these are the 2 big equations relating to light. I don't know how important they are to you, but yeah. So now we can talk. So here's the spectrum of light. So you can see as we increase the frequency, so as we go from like 10 hertz to 10 to the 24th hertz, the energy increases. So radio waves are very low energy. Microwaves are also very low energy, so that your microwave won't kill you. But gamma rays will. So, yeah. And then in this tiny region of the spectrum, we have the visible spectrum. And we have these wavelengths in nanometers. So if I take the product of the frequency and I multiply it by like the wavelength or something, I should get the speed of light. Okay. Okay, so now we can talk about the Rydberg equation, which looks kind of intimidating, but it's not that bad. Okay, so one important thing to emphasize is that the Rydberg equation only applies to atoms with 1 electron. So in other words, it applies to the hydrogen atom, helium plus, lithium 2 plus, etc., right? Okay, so what this says is that 1 over the wavelength. So, okay, so let's imagine an electron going from a high energy orbital to a lower energy orbital, right? So let me think of a good example. So for example, this could be the 2p and this could be the 1s. And there are some restrictions on which orbitals can go to which ones, but we're not going to talk, well, we don't have to talk about that right now. Oh, and by the way, for a 1 electron system, all of the electrons with a certain value of n have the same energy. So for the hydrogen atom, the 2s and the 2p orbitals, for a 1 electron system, the 2s and the 2p orbitals have the same energy. They're degenerate. For multi-electron systems, this is definitely not true, which is why we saw the filling pattern we saw earlier. This is because of like repulsions between electrons and interactions between them. Okay. So let's imagine a transition of an electron from the 2p to the 1s orbital. Now, since the 1s orbital is lower in energy, this will result in a release of energy, and that energy is released as light. Okay. So this is where the Rydberg equation comes up, and so this equation was kind of like discovered by a school teacher in Sweden, I think, named like Rydberg, Johannes Rydberg or something like that. And then it can just be justified by the Bohr model. So this is one of the great successes of the Bohr model. But okay, so what this says is that, so if we have a photon emitted and we know its wavelength, then 1 over the wavelength equals the Rydberg constant times z squared. What's z? So z is the nuclear charge. So it's how many protons are in the atom. So for a hydrogen atom, of course, we only have 1 proton, so z is just 1, so we usually just ignore that for hydrogen. And then we times this by 1 over nf squared minus 1 over ni squared. So where n is the principal quantum number, this number, right? Right? Okay. So I guess we can do an example problem. Okay. Okay. Just to get this point down. Or okay. This isn't super important, but it's good to know. Okay, so let's imagine we have a carbon and then 5 plus atom, an ion. This ion, and let's imagine an electron going from a 3d orbital down to a 2p orbital, right? So in terms of the Rydberg constant, what's 1 over the wavelength of the what's 1 over the wavelength of the electron emitted, of the photon emitted, right? So just break down the equation. So R is some constant, and then can someone tell me how many protons are in an atom of carbon? So the periodic table will be helpful in answering this question. Yep, 6. So it's R times 6 squared times 1 over. So what's NF? Can someone tell me what NF is? Right. So the n of the final orbital. Right. So NF is just 2 squared minus, and then Ni is 1 over 3 squared. So then this is 1 over the wavelength. That's it. Okay, that was just a sidetrack. That's kind of interesting. Okay. since we have some time left, I think it might be a good idea to go over some problems to solidify some of these concepts. So, let me see if I do have some problems. Okay. So this problem is from the 2019 the 2019 Chemistry Olympiad, so the local one. Okay, let me see if I can open it up. Oh no. I don't have an easy way of showing this. Okay, I'll just write it down. I'll write it down. Let's make this really big. Not working. I don't want to delete the periodic table because you might need it. So okay. So so we can use annotate. Okay. So consider an arsenic atom. Okay. Okay. So the question is, how many electrons in a ground state? So that means the lowest energy state of in the ground state. So a neutral arsenic atom, and it's the lowest in energy it could possibly be. In the gas phase, have quantum numbers n equals 3 and L equals 1. So do you guys want to try to do it yourself, or do you want me to walk you through it? So in an arsenic atom, how many electrons have n equals 3 and L equals 1? So let's break this down into pieces. So first, let's write down the electron configuration of arsenic. So who wants to do that? Can someone write down the electron configuration of arsenic? And here's the filling order. That's probably going to be helpful. Okay. So argon, 4s2, 3d10. Okay. So that's right, but I want the full electron configuration. So that's right, but can you just give me the full one? So don't give me the noble gas abbreviation, just everything. It might take a while, but okay, 1s2, 2s2, 2d6, 3s2, 3d6, 4s2. Okay, I think that's right. Okay. So let's look at the first criteria, n equals 3. So then which orbitals have n equals 3? So we have the 3s2, the 3p6, and the 3d10, right? Okay, so that counts the first one. Let's look at the second criteria. So L has to equal 1. Does anyone remember which type of orbital has L equals 1? P? Yeah, that's right. Okay, so now we need to look for p orbitals. So this is the only p orbital we have. So this is the only orbital that actually fills the criteria we need. So the answer is 6, since we have 6 of those. Since we have 6 electrons in those orbitals. So okay, great. You just solved the Yusenko problem. Good job. Okay. Let me see if maybe you can pull up the homework. Okay. So let's just start looking at this because this has some more. So as kind of like homework, what I want you to do is review significant figures. So let me write that down. So-called sig figs. And this is more like related to like how do we treat accuracy and imprecision in science. How do we make measurements? And this stuff is really boring, but it has to get covered. So it would be great if you guys could like review sig figs on your own. So let's just look at some of these problems. So let's look at this one. So what are the three components of the atom and what are their charges, right? So do you remember from the beginning of the lecture? Oh, well, isotopes. Yep. So electrons, protons, and neutrons, right? Okay, so this reminds me we should talk about isotopes very briefly. So this stuff mainly builds on what we've already covered. So let's just look at let's look at oxygen. Can someone tell me what determines what element is what? Like what characteristic of the atom tells me what atom it is? What element it is, right? To determine what element is what, we need to look at its atomic number, right? So that would be the amount of protons it has. But you might remember, but this has nothing to do with the number of neutrons it has. So what do we do about the neutrons? Well, let's say we have two atoms with different amounts of neutrons, but the same amount of protons. So they're still the same element, but they're different. So they're called isotopes. So, right. Okay. So the same element can have different isotopes. So for example, oxygen has two major isotopes, I think. So oxygen 16 and oxygen 18. I think oxygen 17 is stable. I'm not sure. I think it's stable. So yeah. And I just realized I did this wrong. So it should be oxygen 16 and then oxygen 17 question mark. Okay. So can someone tell me how many protons are in oxygen atom? Are in oxygen atom? 8? Great. So we write the number of protons as a subscript, and we write the number of neutrons plus the number of protons as the superscript. And this is what we call the mass number. So let me write that down. Mass equals number of protons plus of neutrons, right? And then all this really is number of nucleons. How many particles are in the nucleus? So can someone tell me how many neutrons are in an atom of oxygen 18? So we're looking for the number of neutrons, right? Great. So we simply take the mass number and subtract the number of protons. So let me clear all of this. Okay, let's do another example. So bromine exists in two major isotopes in basically a 50-50 ratio. So we have bromine 79 and then bromine 81. So if you study organic chemistry later in life, this is pretty important because this shows up in mass spectroscopy. But okay, so that's beside the point though. So let's imagine a bromide ion though. So how many protons are in this bromine ion? Let's just consider this one for now. How many protons are there? So remember that the number of protons is the atomic number, which is given by the subscript, so it's just 35, right? Okay, so now this bromine atom has a negative charge. So that means, so how many electrons would we have to add or remove to get a negative charge? To get one negative charge? Okay. So remember, we can say that the charge So charge, wait, some problems. My stylus stopped working. Okay, so charge, charge equals the number of protons minus the number of electrons. So we have the charge of -1 equals 35 protons minus how many electrons? Okay, so we have 36 electrons. Does that make sense? Okay. So now we've determined that, okay, so we have 35 protons and 36 electrons. Now all that's left is to determine the number of neutrons. So does someone want to tell me how many neutrons there are in this bromide ion? So for the number of neutrons, all we have to do is take the mass number, which is okay, so remember that the mass number is the sum of protons and neutrons. So if we want the number of neutrons, all we have to do is take the mass number and subtract the number of protons. So that's 81 minus 35, so yeah, 46. I think that's right. Okay. So, okay. So now you can just apply this to any ion you see. And if you look at the homework, there's a table I want you to fill out. So, yeah. And I also posted the answers. So, yeah. So now we have just a few minutes left. So I think it would be great if anyone had any questions, you can just ask them right now. You can unmute the microphone if you want to ask a question.
Where do you check the homework?
Can you speak up?
Where do you check the homework?
Oh, it's in the Dropbox.
Dropbox.
Oh, I just realized you can see all those notifications, right? Yeah, this is not my laptop, so those are not my Roblox notifications. So, okay. Is that the only question we have? Yeah. So it seems like this is just about time. So, yeah. So I don't think there's too much to cover right now. So at this point, all you guys need to do is you just need to practice. So, yeah. So just fill out this table, and it might seem like a lot of work, but it's not that bad. So I think that's it. So see you in a few days. Okay. So have a nice night. And then if anyone has questions, just ask them now.